Thank you all for attending the talk today. I'll be presenting our work, A Cautionary Tale, on the role of reference data in empirical privacy defenses. This is a joint work by myself and colleagues at INRIA, SAP, and Accenture. And to support open science, we have the artifact reproduced badge. As the previous talk explained well, differential privacy can be introduced into the training of a machine learning model to protect the data's privacy. And the epsilon that results after using differential privacy can be thought of as an upper bound on the privacy leakage. Also, there can be a practical epsilon that would be assessed using an empirical privacy attack, often a membership inference attack, and this practical or empirical epsilon can be thought of as a lower bound privacy leakage. As these empirical privacy attacks are used to quantify this lower bound privacy leakage, there have been empirical privacy defenses that have been proposed to protect against these type of real-world attacks. The most simple example would be just using L2 regularization, where the weights of the model are constrained during training, and this protects the underlying privacy against an empirical privacy attack more than if L2 regularization weren't used. However, there's been many other more complex empirical privacy defenses that have been proposed, and they often make an assumption that in addition to the training data, they'll use a second data set that comes from the same or a similar underlying distribution as the training data, and this data set would be called reference data. However, despite reference data being integral in the design of many of these empirical privacy defenses, its own privacy has often been an afterthought. Here we can see 6 very well-known empirical privacy defenses, and our paper as the 7th on the bottom. We can see that oftentimes the privacy of the reference data isn't discussed or analyzed, or if it is analyzed, it may not be sufficient for reasons I'll show in the next slide. Here, we can see a utility privacy curve that's generated for the empirical privacy defense called adversarial regularization in blue, and a second version of adversarial regularization in orange that we discuss in our paper. We can see here on the x-axis the model utility or test accuracy, and on the y-axis the membership inference attack accuracy or privacy leakage. This utility privacy curve can be generated because empirical privacy defenses have a parameter that can be tuned to add more utility or more privacy. However, when looking at this graph, right now we're looking at the privacy leakage only with respect to the training data. And it should be clear that given that the best model would be in the bottom right-hand corner, having the most utility and the least privacy leakage, the orange curve is strictly better than the blue when only looking at the training data privacy leakage. However, these are the utility privacy curves when the privacy leakage with respect to the reference data is also assessed. And what we can see is now no concrete statement can be made about which is the better defense. We can see that the orange curve, it will have better model utility and less privacy leakage with respect to the training data, but the blue one has less privacy leakage with respect to the reference data. So the key point that we want to make is that really in order to assess one of these empirical privacy defenses using reference data, the model utility, training data privacy leakage, and reference data privacy leakage all need to be assessed and probably explained the training and reference data relative privacy before actually using the method. In order to better understand these empirical privacy defenses, we propose a baseline called WERM. Our problem statement is formulated where we have a data set D that's comprised of the union of the training data, DT, and the reference data, DR. Similar to standard empirical risk minimization, we want to minimize the loss function over LD. However, we introduce 2 constraints. These are constraints on the generalization error with respect to the training data and the reference data, in this case CT and CR. The reason we constrain with respect to the generalization error is because a black box membership inference attack is really trying to understand how the output of a model differs on data that it was trained on compared to data that it wasn't trained on. And this is what the generalization error can quantify, the difference in performance on training data and unseen data. After some manipulation, we end up with this simple equation on the bottom, which is just a weighted ERM, where W is the weight, and W will provide the weight for the L of DT during training, the loss in the training data, and L of DR, the loss in the reference data. So in the case when W is 0.5, this would mean that both losses get equal weight and we're weighting all data points equally. However, If we select a W that's not 0.5, then we'll add some weight, more weight to one of the data sets compared to the other. Why this is a useful baseline and it is interpretable is because it's the first empirical privacy defense that provides theoretical guarantees. First, we provide guarantees on WERM's utility. We derive this equation called N effective, which is the effective data set size. Here we can see that it's solely dependent on W and the size of the training data, NT, the size of the reference data, NR. So when NT and NR are equal, this would mean that using a W of 0.5 would result in an effective data set size being equal to the total data set size, which would mean that the model utility would be maximized. However, using a W in that case not equal to 0.5 would mean that the utility would not be maximal, and then there would be some trade-off with the privacy. So we also derive guarantees on its relative privacy. And this is an important point, that the relative privacy is the relative privacy of the training and the reference data. We're not using this with differential privacy. However, to derive these guarantees, we conduct a thought experiment where we say, what if we train WERM with differential privacy, like DPSGD? Then we would end up with a resulting epsilon value, epsilon 0. And we can see that if we did that, we would derive these epsilon values, epsilon t and epsilon r, which would be the privacy with respect to the training data and the privacy with respect to the reference data. But since we're interested in the relative privacy, by dividing epsilon t and epsilon r, epsilon 0 will disappear, and we see that we actually have these values where it's only dependent on W, the weight, the size of the training data, NT, and the size of the reference data, NR. And what's interesting about these quantities is while we conducted this analysis here for the training and reference data of two data sets, these guarantees actually hold for the case where every data point is weighted independently, so if every data point has its own distinct privacy considerations. To better understand these theoretical results, we have this plot where we can see the effective data set size on the x-axis. So in this case, the training and the reference data both have 10,000 data points. And again, the effective data set size corresponds to the model utility. On the y-axis, we have this theoretical privacy with respect to epsilon t and epsilon r, the training and the reference data. And we look at values of W between 0 and 0.5, where 0 would give all the weight to the training data during training, 0.5 would give equal weight. Starting on the right-hand side of the graph, we can see that in the case when W is 0.5, we would expect that the model will have maximum utility because it will weight all data points equally, and therefore the effective data set size will be equal to the overall data set size, and the privacy leakage with respect to the training and reference data will be equal for any value of epsilon 0 if we were to use differential privacy. However, by shifting to the left of the graph, we can see that now we're lowering W closer to 0, and by doing so, we're giving less weight to the reference data, which of course there will be a trade-off because we're going to use the reference data less while training, so it will have less privacy leakage, and that will result in more privacy leakage for the training data and less model utility because the effective data set size will decrease. The reason this is an interpretable baseline is because the experimental results align well with the theoretical results. Here we can see the experimental utility privacy curves with the test accuracy on the x-axis and the membership image accuracy on the privacy leakage on the y-axis. If we look at the far right-hand side where we see the blue curve, this would be our baseline method, WERM, and the furthest point on the right would be the case where the squares representing the training data privacy leakage and the crosses representing the reference data privacy leakage overlap, and we can see that that means that it will have the experimental results show that it will have the largest model utility, and the privacy leakage on the two, when assessed empirically, is equal. And also, by shifting W from 0.5 to 0, we can achieve any possible privacy setting depending on what the relative privacy considerations are before training. Looking at the other methods, these are other state-of-the-art empirical privacy defenses using reference data, we can see that they don't do a poor job of trading off the reference data. So they're not really able to trade off reference data privacy for training data privacy or model utility. So they're only operating in one privacy setting, which is the case where the reference data would be considered extremely private, which is a viable case, but depending on the setting, one may want to consider the other data set more or less private. And it also outperforms these other methods in the majority of these privacy settings. if one were to actually use an empirical privacy defense as a practitioner, it would be important that this desired relative privacy between the data sets that one is using actually has a correlation to the resulting privacy that one would assess with a membership image attack, so that real-world privacy leakage. Here we can see this correlation analysis where, based on the parameter that controls the utility privacy ratio during training for these empirical privacy defenses, and the actual empirical privacy ratio as measured by the membership image attack, the RWRM on the data sets we analyzed has a near perfect correlation, suggesting that the desired ratio that one would want before training will actually result after training. Alternatively, these other methods don't seem to be able to map so well, given a desired ratio to the empirical ratio. So to conclude, overall, we conduct the first comprehensive evaluation into how these empirical privacy defenses perform with respect to all three relevant metrics, whereas previously only the model utility and the training data privacy leakage were looked at. Our method, WRM, is an interpretable baseline that we believe any empirical privacy defense using reference data probably should at least compare against it, because it's simple and interpretable, and if it can beat it, then it really shows that the proposed method is working. Interestingly, this baseline actually outperformed a lot of these supposed state-of-the-art defenses, which is exactly why it's important to have baselines and to measure against them. And perhaps most importantly, our theoretical results, they lead to a better understanding of the privacy implications when multiple data sets with different privacy considerations are used to train a single global model, because it can often be the case even in federated learning scenarios where different data sets can be considered having different levels of privacy, and if one isn't using differential privacy, perhaps you would still like to know what is the privacy leakage associated with each of these. Thank you for your attention. I'd be glad to take any questions.
Any questions? No one? Oh, please go ahead. Maybe wait for the microphone.
No, I can speak loud.
No, for the recordings, we have online people as well. It's coming.
So, your approach, does it describe how to actually generate the reference data set, or you assume that there is a mechanism to generate the reference data set?
So, our approach doesn't propose the notion of reference data. We really took it as a fact in the sense that these are existing empirical privacy defenses. They assume access to reference data. So given that assumption, can we propose a baseline, and that's where we started from. So there are some, to further answer your question, I have a slide here. These are some examples of perhaps real world reference data availability. So there could be large publicly available data sets, for example. In this case, it's actually the opposite of what the existing methods are doing, because if you could train a method just using publicly available data that works well on your private data set, why would you even use the private data? So this is an example. There's also these business models where there could be the same data set coming from the same distribution, but one has more privacy than the other, and there's a few examples here.
So to kind of follow on, one of the things that's interesting that I did not get the intuition for is, can your approach help define that reference data set, like generate a better reference data set using some of the observations that you made in your work itself?
I wouldn't say that it can help generate a reference data set, but what it can do is, given there would be different relative training and reference data privacy settings. So given some of these examples, the reference data may be considered more private and the training data less private. So if one were to have some reference data, they would hope that the resulting model would protect the privacy according to that desired ratio. And what we showed is that our method has a very strong mapping between that, what you would want, and then what you result in.
Thank you.
I suggest we thank the speaker here, and if you have further questions, we will have a coffee break. Shall we thank you?
Thank you.
Our